Nice. That's frustrating. This is for Jimmy Donnie. Sweet. Hello, everyone who's in the chat. Hey, Sarah. Let's get started at 10:20 as planned. There's no do now. We'll just, get out your sheet and read it. Remind yourself what it's asking. So when we go over it, it'll make sense. Sarah, are you working on the discussion prompts, or are you sitting this round out? Because I know it was hard, and Luca's the only one that's really turned in anything. Good morning, Justin. It's good to see you. It is hard. I know. I felt a little mean writing those down, because the prompts that Professor Myers put out are a lot easier, I think, but I don't think they explore the concepts in depth enough, so I wanted to change it. Yes. So the number for question 2, Sarah, I would highly recommend watching the last part of the last lecture to help with this. Like the part where she talks about it is pretty insightful, I think. Good morning, Yona. That applies to you too, Yona. Good. Hey, Chris, Ethan. Wow, double Ethans. Hello. The second question is super complicated. Let's see. Democritus and his teacher Leucippus make a bold anti-Parmenidean claim in saying the world is made up of only two things. But we must remember that Parmenides' claim was about not being in the existential case. When Leucippus and Democritus identify the void, they identify it as a null only in the predicative sense. They strongly maintain that it exists in the existential case. Yeah, because they're saying the void exists. Can you explain the argument in more detail? Which premise in argument A are they? Because I feel like the first question is more of a personal opinion. Yes, and I'm letting you argue either way, because there is an argument to say that birth, life, and death are predicative, and there is an argument to say no, they're actually existential, if you just talk about the concept of being. But B is, question B, I'm really trying to train you as a thinker, right? As a philosophical thinker, to really take a stand and argue something, even if you don't agree with it, I guess. And we have 30 seconds left. Good morning, Atune. Grandmaster Itamar, good to have you back. Even though I saw you Saturday, I'm still sorry about leaving, guys. Sarah, Yona, Itamar. I feel bad about it, but yeah, my sister's such a flake. I never see her. She lives in California, so it's extremely hard to get a hold of her and stuff. So, yeah. I still feel bad about it. I'm sorry. All right, it's 10:20. Let's get started. All right. So I think going over this sheet will take around 5 minutes, if that, and then we can go on to the next topic. And I'm not really well versed in like switching cameras, so we're just gonna do the lesson on this whiteboard. So you're never gonna see my face today. Okay. I would appreciate that. Yeah, please fill me in. Okay. So here we go. The direction of the magnetic field at the indicated points in space. Where would the 3D compass point have placed at the indicated points? All right, so I saw a couple students do this. This isn't wrong, but it wasn't what I was looking for. All right, so if my current goes this way, it's clear the field goes behind the wire here, out of the page, and then in front of the wire, and then into the page and then back, right? This is a 3D version of it, but I didn't want that, right? What I really wanted was, hey, if I place a compass at point A, where does it go? Well, it would go out of the page. If I place a compass at point B, where does it go? Into the page. That's all I wanted, right? And actually, everything on this side of the wire is out of the page, right? And everything on this side of the wire is into the page, right? Because it's coming out and then going back in, going underneath the page and then coming right back out here. This is just a super thin slice of a cross section, right? Okay. Now, good morning, Eric. Good morning, Dimon. Wire normal to the sheet, current moving out of the page. So now my current's coming out this way, which means my field goes this way, right? So I could draw those circles, right? But instead of drawing these circles, right, what I'm really going to do is say, hey, here, the field points this way, here, the field points this way, here, the field points this way, here, the field points straight up, straight to the right, diagonal, diagonal. B and A are the same direction. The only difference between A and B is the field here is weaker than here, right? Because it's farther away from the wire, right? Super simple. It's like, hey, if I place a compass here, where's it going to point? Boom, there. If I place a compass there, where's it going to point? Boom, there. Okay? Okay. So let's go to number 3. Okay? Again, it's the right-hand rule, right? And if my current's going this way, then all on the inside it points in. And that includes point B and point C. All right, and all around the outside, and this includes point A and D, points A and D, the field points out of the page, right? All this is a curved version of number 1, right? So if you get number 1, you should definitely get number 3. Please let me know if you have questions, because I know we are moving fast. Today's going to be a fast day. Okay, lastly, number 4 is literally if you took this solenoid and turned it not this way, because the current's going that way, right? So I want to flip it this way. So this side gets to the front, this side gets to the back. Okay, let me show you that again. This side will face the front. This side will face the front, this side will face the back. Right, so I'm flipping it this way. So if I have here, like this, right? So if I have this, I'm turning it this way, right? I'm turning this thing this way, so it faces here, okay? These are 3 of my cousins. Do you remember when I told you that all my cousins our names start with the same letter? I wasn't kidding, all right? So here you can see that's Andrew, that's Alan, and that's Anthony. Yeah, they're all older than me. Alan's older than me by 2 years. Anthony's older than me by 4 years. And Andrew's the oldest. He's, I think, 6 years older than me or something. I've lost count. Anyways, so why did I use this? Because we're turning it this way. We're not turning it this way. Okay, we're turning it whoop, this way. All right, and when we do that, what you'll see is everywhere outside of this solenoid, the field's going to point down, right? Right, it's all down, right? All around, it's going to be down, right? And that means point A and B, we're going to point down, right? Now, point C, if it's also, whether it's in front of the solenoid or behind the solenoid, it would also point down. But in the instance where point C was inside the solenoid, it would point up, right? And if you want to actually draw the field lines, instead of drawing, hey, what would a compass do here? We would get our familiar eggplant or bell pepper shape, right? Everywhere it's going to look like this, right? And it's pointing down, 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 and then this points up, right? Inside will point up. The cool thing to note is that the field lines here look exactly like what we call a bar magnet with a north and a south pole, all right? And here, and now that we've gone over the solutions to this, now is when you're going to have to start taking some notes, all right? So I want everyone to get out their notes. I'll give us around like a couple minutes. I want you to draw this, okay? And we're going to learn our first thing of the day, all right, before we go on to a new page. Good morning, Caitlin. It's so good to see everybody. Oh, this is bitter, a little bit more bitter than I would think. But does the bitterness lead to a cleanliness? I'm not sure. Okay. So I hope we all have our notes out. A really important distinction you need to know, and a convention that we follow, is that magnetic field lines point out of north poles, and they point into south poles. All right, so there's the convention, right? Oh, there's my north pole because my field lines are pointing out of it. There's my south pole because fields are pointing into it. It's kind of like a positive negative charge, but not exactly, which means if my solenoid acts like a magnet, right, then I would say my north pole is somewhere around the top and my south pole is somewhere around the bottom. Is it always top bottom? No, because I could flip this solenoid upside down and then the south pole will be at the top. And right, so north south is not about top or bottom. It's about where the field points out of and where field points into. Okay. Why is that? Anyway, all right. So now we can get into some bits about random convention. Okay, and to do that, I need to find a blank page first. Wow, look how far we got. This is all of our circuit stuff. Wow, so much fun. Whoa, we've done a lot. Okay. Okay. So, why did we call them north and south? Okay. So, the first thing we have to go over is a compass. All right, I'm going to start using a pen now because it's easier to read. All right, so we have a compass. What is a compass? All it is a magnet. A compass is a bar magnet. That is free to spin. Okay, so for a standard magnet that you have, it's literally just like a super light magnet, and it has like a very low friction pivot, and it's attached via an axle to some point. A super basic one everyone can make in nature is like a magnetized needle, like a sewing needle. You put it in a cork, right? So here's my piece of cork. Here's my needle, right? And then you put that in some water, all right? And that cork floats and that needle's magnetized, and then it's free to rotate in any direction you really want, okay? What we noticed, right, through nature is every point, like, so there were every magnet has two poles, right? I call it an A pole and, okay. So the first thing a compass does is it aligns with the magnetic field, right? So a compass will always align itself. Okay, how do you magnetize something? We're going to go over that tomorrow, all right? Is the Earth a solenoid? We're going to go over that Wednesday. All right, so it aligns itself with the magnetic field, which means if I'm in a region of magnetic field that looks like this, right? Right, if I put a compass here, what's it going to do? The needle is going to go this way. If I put a compass here, what's the needle going to do? It's going to go this way. If I put a compass here, what's the needle going to do? It's going to go this way, right? So not only will it always become parallel with the magnetic field, we noticed another thing, all right? If my field looks like this, and I place a compass and it looks like this, okay? It'll rotate this way, or it'll rotate the other way. It doesn't matter, but it always rotates so that it ends up, this is my initial position. It'll end up like this in its final position. But not only that, all right? If I mark this end A and this end B, it'll always be A that faces up. Like when it and if I move it back either this way or if I turn it, so if I turn this needle, okay, oh, all right, cool. So if I turn this needle back to its original position, it'll always go this way. And if I turn it back to this position, it'll always go this way. Like point A is always going to point towards the top. It'll always orient itself so it's A, B. It'll never orient itself so it's BA, right? So not only is it always parallel to the field, one end is always pointing north. It's there's nothing special about it. That's just something we realized. Like, oh, like I noticed one end will always point north. That's it. I don't know anything about what's inside that makes it do that, but the same point always points north, and the same point always points south. What do you think we call those? We call them the North and the South Pole. Yeah. So anytime a compass does this, I will call this the North Pole, and I'll call this the South Pole. Why? Because the North Pole always points north, and the South Pole always points south. What we actually see is the more magnets we have and the more compasses we have, but they all behave this way. They all have an end that always points north. So what do we call that? The north and the north and the south and the south. And I have a mystery magnet. I've never played with it before. Which side is north? Which pole is north? Which pole is south? I don't know. There's only one way to find out. You let it rotate, and once it rotates this way, and ends up like this, okay, cool, then that's my North Pole and that's my South Pole. That's the convention we're using. It's completely random that we chose to name them this way. There's nothing special about the poles that make them this way, right? But once we have that convention established, we notice some cool things, okay? We notice that North Poles always repel other North Poles, right? So if I have two compasses, and I don't know their poles. I don't know anything about them, but I put them like this, okay? Boom. And I see them rotate boom, this way, right? All right, now I know that if I ever did this, they would repel, right? Because no matter what, so here are my two random magnets. They go like this. I know these are north poles and these are south poles. So now I know if I ever do this, they'll repel. If I ever do this, they will also repel. And if I do this, they attract. Okay? So the other thing we observed, and this isn't like, these are all observations. I'm never going to explain to you why this happens. These are all just observations. Oh, I'm so sorry. Okay. Okay. So we noticed that not only do one side always points north, and the other always points south, right? We call these north and south poles. All right? So that's our first observation. Our second observation is then like poles repel, and opposite poles attract, right? Which leads us to a very stunning discovery of it leads us to a very stunning discovery. If you want to go into why this is true, right, or a little deeper, all right, let's look at observation 2 a little deeper, okay? It's really not the magnets exerting forces on each other, it's the magnetic field, right? That's the field is always the source of the force, right? So if I'm saying, if I have a region of field that looks like this, right, and I place a magnet here, what's it really going to do? Is it going to which way is it going to rotate? It's going to well, it depends. If this is a north pole and this is a south pole, it'll rotate this way. If this is a north pole and this is a south pole, it'll rotate this way. Whatever it is, its final position will always be north here, south here, north here, south here. Right? The magnets, they will align themselves right, such that going all the way back here to our first convention, that field points out of north poles all the way to our first convention, that field points out of north poles, field points into south poles. That's the lowest energy configuration here. And systems always will gravitate towards positions where they have low energy, right? So I want field to point out of my north pole. I want field to point into my south pole. I want field to point out of my north pole and into my south pole, right? Such that the magnetic field points out of the north pole and into south pole, right? So it's not, sure, is there a south pole here from some random magnet and that's attracting the north pole? You can think about it like that, but almost like the situation with electric field where I had uniform electric field, like, yeah, I don't care where that field's coming from. I just care that the field is there, right? So do I want to think about a south pole here? Not really, right? It's just going to align itself with an external field this way, okay? Now, but that allows us to talk about a really big kahuna, all right? Because if I'm on Earth and all of my magnets align this way, where this is north, 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 south, 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 south. What does that say about the field lines of Earth? It means the field lines are pointing all up. This is Earth, which means Earth's North Pole is here, and Earth's South Pole is here. So Earth acts like a giant bar magnet, but its geographic north corresponds to its magnetic south pole, and its geographic south corresponds to its corresponding north pole. This may seem weird at first, but I really want you to realize that this isn't weird at all. This comes as a natural and inevitable consequence of how we defined a north pole in the beginning, right? If we define a north pole of a magnet, the pole that points towards geographic north, well, that by definition means my geographic north is my magnetic south, because like I defined this pole as north because it faces north. But those are the poles that are inevitably attracted to a south pole, right? So we kind of shot ourselves in the foot by defining north pole, magnetic north pole in that way to begin with, right? Like the Earth has a south pole here because we said, oh, all these magnets have the same end facing north. I'm going to call that north. But guess what? All those north poles are always going to be attracted to south poles, right? So, Ainava, that's a super complicated question that we don't really understand yet. All that we know is that the magnetic poles do switch locations on Earth every like couple 10,000 years. We don't know why. It's too complicated. That's one of the things that we know it happens, and we just don't know why. It has something to do with the core, the moving iron currents, and the molten iron, but we're still not super sure. And it's really going to mess things up because we have a lot of scientific evidence that shows that birds migrate and align themselves with the magnetic field. So when the magnetic field switches direction, not only are all of our compasses going to be broken, I mean, that's not a big deal. We'll just like repaint our needles, right? But the birds will have trouble migrating. Dogs also, when they poop, um, dogs will always align themselves with the magnetic field. They will always face north when they poop. Is every dog now going to face south when they poop? Who knows? It doesn't happen in an instant. It takes like it's on a geological time scale, so it'll probably take it'll change over the course of like 100 years or so. And during that 100-year period, the magnetic field is hypothesized to get a lot weaker, and that's dangerous because the magnetic field itself shields us from a lot of radiation. We're going to get into that a little later. All right, there's some basic stuff about magnetic field. What we're going to do now is going to look at what other things the magnetic field influences, right? So we've seen the magnetic field, right? So the B field, what does the B field affect? Right? One, magnets, right? They will always reorient themselves, right? They will reorient themselves. Reorientation, like you know, so the North Pole, the field points out at the North Pole, and the field points into the South Pole. We'll always do that. The other thing is much more important, okay? And it goes into this thing. I want to remind us about gravity, okay? Right? And more importantly, I want to talk about gravitational field. All right, what is the source of gravitational field? Well, objects with mass, right? And what does gravitational field affect? Well, I would say objects with mass. It's that simple, right? If we talk about electricity, my E field. Well, what is the source of E field? Well, objects with electric charge. Q, right? Well, what do they affect? Well, objects with electric charge. Q. The same thing can be said about magnetism. B field. What is its source? Don't say magnet. It's moving charges. Charges that move. Create magnetic field. This is our right-hand rule, right? Right? If I have a current-carrying wire, it will exert a force on an object. I mean, it'll have a field, and that field wraps around it. It's circular, blah blah blah. Now I want to think about what does the magnetic field really affect. I don't want to think about magnets, right? This analogy still holds true, moving charges. Okay? Ah. Yes, the reason why magnets are affected by magnetic field is because they have moving charges inside them. Exactly. Okay? I want you now, the formula for magnetic force is as follows. The magnetic force on a moving charge, okay, is equal to the charge itself times its velocity. So here already we see, okay, and it's cross the magnetic field. So you could think of it like this, right? Charge times field. Except some component of my charge has to deal with velocity now because it's a moving charge. It's not just an electric charge, it's a moving charge. So it's the same thing as like, oh, my quantity times my field. The other thing before was mass. So what's my force? Well, mass times the field. The other thing was electric charge. So what's my force? The electric charge times the field. Now my thing is moving charges. So what's my force? It's the moving charge times the field. So I need some way to quantify that movement and its velocity. So here you can see if I have a stationary charge with velocity 0, there's no force, right? So the force only exists if the thing is moving. The tricky thing here is this right-hand, this cross product, okay? So in your notes, to the best of your ability, I want you to draw this. This is our new right-hand rule, okay? Okay? Hey, okay, like this, okay? Upside down, what up, hey? So it's almost like you're playing, like how little kids play with guns. That's completely inappropriate. Bang, 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 bang. So you're doing that, but you're adding a third axis, okay, like this. Okay, yikes. Okay, like this. So I want you to draw that in your notes to the best of your ability. I'm going to draw it here, right here. Here's my pointer finger. Here's my middle finger. Here are the two other fingers. And here's my thumb. Cool. Right, and what you really want, your whole goal is to, it's actually a really bad image, but I can do it again. Hold on. Come on, Alex, you went to art school. You gotta do better than that, okay? No, that's not good either. But you get the drift, right? And their whole goal is to create a set of principal axes that are all parallel, that are all perpendicular to each other, right? So there's my x-axis, there's my y-axis, there's my z-axis, all right? So your three fingers have to form the three axes, okay? Which means every finger needs to be right. This is a right-hand rule. This is, thank you, Itamar. A star. You guys are all stars. You guys are my stars. A way to double check if you're doing this right is to see if your every finger needs to be perpendicular to the other two fingers. So is my pointer finger perpendicular to my middle finger? Yeah, look at that right angle, beautiful. Is my pointer finger perpendicular to my thumb? Yeah, look at that right angle, it's beautiful. Is my middle finger perpendicular to this one? Yes. Is my middle finger perpendicular to this one? Yes, right? Look at this 90 degree, hold up, there, right? Look at that 90-degree angle, right? My middle finger and my thumb. Now, is my thumb perpendicular to this one? We already established that, yes. Is my thumb perpendicular to the middle finger? Yeah, we already established that, right? So all three axes have to be perpendicular to each other. And here's how I label them, okay? Your V goes here. Q times V goes on your pointer finger. Your the field goes in the middle finger, and your force is on your thumb. Right? You can draw these with a marker on your fingers if you want to remind yourself, whatever. All right? So this is the rule. Okay? It means not only do you need speed, not only do you have to be moving to experience a force, not only does there have to be a magnetic field there to be a force, there needs to be some component that's perpendicular. For instance, if my field goes this way, right, and my charge goes this way, its speed, guess what the magnetic, guess what the magnetic force on that particle is, right? Here's the field. Here's my speed, v, my velocity. Guess what the magnetic force on this particle is? It's 0. Because there's no component of its velocity that's perpendicular to the magnetic field. And this is a type of problem, and this is a type of force because there's a cross product. I'm only going to have magnetic force if I have a component of my velocity that's perpendicular to my field. That's same thing as torque, right? Torque is R cross F, right? Only if this is my R, right? And I exert a force in this direction, there's no torque there. It's not going to spin, right? I need some component of force here. Same thing here. So, and this is where it gets really weird, okay? So let's look at the extreme case where I do have magnetic force because my force is my velocity is completely perpendicular to the field, right? So let's say I have a region of magnetic field that looks like this. Right, here's my magnetic field, it's uniform. Yep, and let's say I have a positive charge and it's going this way. Well, now I have the case where they're perfectly perpendicular. So whenever it's perfectly perpendicular, not only do I have a force, the QV cross B simplifies to QVB, right? Because it's really QVB sine theta, but my theta is 90 now. So it transforms into this, right? Because theta is 90 when they're perfectly perpendicular. That's my magnitude. The cooler problem here is like, well, what's the direction? For all of these types of problems, I'm going to give you the direction. So the direction of 2 of F, B, and V are given. All right, so all you have to do is align those 2 corresponding fingers with the direction. So I'm going to use my right hand here. If the B points up, my middle finger is B, right? According to that diagram, right? According to my convention, right? My middle finger is B, okay? So my middle finger will point up. My velocity is my pointer finger. That points to the right. Cool, it's already doing that. So my answer, where's my force point? Straight out of the page. Look at my thumb. So basically, this particle is going to want to do, so the force points out of the page. That's the answer. Okay. So this particle is it's traveling this way. It's going to want to do this, right? It's going to want to come towards us. It's going to turn this way, right? Whoosh. Okay. I'm going to post this right at noon. This is your assignment, okay? And I'm going to do number 1 with you together, okay? In each of the following scenarios, there is a region of space with a uniform magnetic field. A charge is sent through the region and experiences a force FB. The direction of 2 of the quantities will be given. Determine the direction of the third quantity. So again, in this problem, I have a positive charge moving towards the right. So my pointer finger will move towards the right, okay? The field points into the page. So my middle finger is now pointing into the page. So where does the magnetic force point? It points up, right? My thumb, the force now points up. Okay, that's an example of how I would do question A, right? Cool. The other thing I'll tell you right now is it's QV that points in your pointer finger. So guess what? If I have a negative charge and it points this velocity points this way, guess where QV points? QV points this way because it's a negative charge, okay? If you don't want to worry about that, anytime I have a negative charge, just use your left hand. And it's much easier to do it that way. So let me give you an example. If I have a region of field that points out of the page and my velocity points up, but it's a negative charge, negative charge, I'll either do it this way. So if the V points up, but it's negative, the QV points down. The field points up out of the page, that's my middle finger, so my force points to the left. That's my answer. I could have also just used my left hand. Points up, field points out, and look where my thumb points. My thumb still points to the left. All right, so if you don't want to do the switcheroo, use your left hand anytime there's a negative charge. If you only want to use one hand, just make sure you got to switch the direction every time there's a negative charge. That also goes for the field generated by a negative electron current. I'm going to be using my left hand for that too. Okay, so negative charges left hand, positive charges right hand. If you guys want some centripetal force review, the second problem is a problem that combines centripetal motion and magnetic force. Now, why is centripetal motion even relevant to these types of problems? Let me show you. Let's say I have a region of field that points straight into the page like this. Okay? And I have a particle that goes, it's shot this way. It's a positive particle, it goes this way. Well, where's the force on that particle point? I want everyone to get their right hands out together, all right? Let's do this together, okay? My pointer finger has to point in the direction of the velocity, okay? So it points this way, okay? My middle finger points in the direction of the field, which is into the page, points this way. So where's my force point? With my thumb. It points straight up, okay? But guess what? If my force points up, then my velocity is it's gonna turn my particle this way, isn't it? Right, so a split second later, my particle is now here, and it's traveling in this direction, right? But let's do our right-hand rule again now. If I'm pointing this way, my field points into the page. Look where my thumb points this time. My force is now here. And again, that means a split second later, my particle is now here, and it's traveling in this direction. And its force, where is it going to point? This way, this way. Oh, it points that way. My force is always going to be perpendicular to my velocity. Right? Because I'm basically, my particle's doing this, right? Whoa, and my thumb is always pointing, right? My thumb is always pointing in the perpendicular to my pointer finger, which is my velocity. So the force is always going to be perpendicular to velocity. And this is an example of centripetal motion, isn't it? My force is always perpendicular to my velocity. So it's a circular motion, right? So when I have a charged electric particle with a velocity, and its velocity is perpendicular to the magnetic field, that particle is going to start moving in a circle, right? So what I can write is FB equals mv squared over r. And what's FB? Well, that's QVB. Whoa, I thought it was V cross B. Yeah, but guess what? V cross B turns into VB when they're perpendicular. And if my velocity is confined to this paper plane, and I'm defining my magnetic field as perfectly perpendicular to that plane, well, they're already perfectly perpendicular, right? It will never come to rest, right? It's just going to keep, unless it slows down. How will it slow down, though? How is it going to slow down if there's no force pointing anti-parallel, right? Because to slow down, remember, to change my speed, I need a component of my force or acceleration parallel to the speed, and I don't have that. My only force is perpendicular, and that's only going to change the direction. Okay, that's what I'll leave you with. We're gonna review today's fast-paced. All right. So we're really gonna blitz through magnetic field and magnetic force, and what that means is there's going to be there's going to be practice now every day. There's going to be homework every day, but it's going to be a little lighter, all right? So, just like the last practice we went over today at the beginning of class was really light, same thing here. So what I will say is this is really light. This is what's due tomorrow, okay? This is a challenge. This actually takes long, but what I will tell you is we're going to go over it first thing tomorrow and use that as a launching point for the next lesson as well, okay? So don't worry about it if you can't get it, all right? That's what I'll leave you with. I got to go start my Regents stream now. Have a great day. Um, and yeah, see you soon. All right, see you tomorrow. Bye.